A great way to get a handle on the implications of our theory are to look at some example solutions to the time-dependent Schrodinger equation. So what I've done actually is I've gone ahead and built a computer programs so that we're going to look at some computer solutions to the time-dependent Schrodinger equation. So I'm going to look at computer solutions for the wave function psi of x and t under various conditions. And then what we're going to do with those computer solutions is I'm going to show you the resulting probabilities for finding the particle at any location x at a given time t, which of course once we've solved for the wave function we can get from simply looking at the square of the wave function. So the first example I'd like to look at is what happens if I make a Gaussian wave function. So I'm just going to start with a Gaussian wave function, and I'm going to let it evolve in time according to the time-dependent Schrodinger equation. So here I've got a movie I can show you. Here, let's play this. And what you notice is, and I'll let this repeat a bit, but what I hope you're seeing here is that it starts out, right, with a very narrow peak. So this is something beginning maybe to approach a pure state. And then as I let the time-dependent Schrodinger equation evolve my state, you notice the probability just begins to spread out, just as we've been predicting from the beginning of the semester, due to the fact that in this initial state, I have a significant localization of my particle, and as a consequence, a wide spread or uncertainty in the momentum, and as time goes on, of course, that means the probability of where I can find the particle begins to spread out. So that's the first key demonstration. Now, that Gaussian wave packet was something like, psi of x at time t equals 0 was just some simple e to the minus x squared over 2 sigma squared. I'm not being super precise about the normalization. Now, we can try something else. What if I take a different form? Let's start with the same kind of an idea. This is at time t equals 0, of course, that I'm writing, but the same type of an idea, except what I'm going to do now is I'm also going to give some waviness to it. I'm going to build in a certain wave vector to it of size k0. And you might wonder, well, what will that do to the state of my system? So if we go to the second movie now, you'll see what happens. So you'll see the same packet, except now I've multiplied it by this phase. Of course, when I take the magnitude squared of this wave function, right, the phase would go away, at least at time t equals 0. And then I'll just see exactly the same peak. But the big question is, what is it going to do now? Right? We should expect, again, from uncertainty arguments, it should spread out. But will it do anything else due to including this sort of wave-like nature into the wave function? So here's what we find in our next movie. So what you'll notice is now, right, the particle, we've actually gotten it to move. It starts off the same, but as time goes on, it moves along here. Now, one thing I'd like to stress for you is that notice as the wave function gets to the very edge of my window where I'm looking at it in my plot, right? So again, this is the position of the particle going across this axis. This is the value of the wave function moving vertically. When he gets to the very edge, you'll notice his little end there leaks over into the beginning. What I've done here is I've applied in my solution a mathematical trick called periodic boundary conditions. I've basically sort of cut out this one length of space and taped it back to itself. So when this wave function gets to the edge of my screen, instead of just going off the screen, it wraps around back on the other side. But I just want you to see that so you understand what you're seeing. So you see I have it now moving along nicely. The other thing that you will notice is that indeed, even though it's moving, it is still spreading out because I don't know exactly everybody's momentum. Their momenta are definitely centered on h bar k0, but I really just don't know the exact value of it. Now, we can try another example here. If I can try exactly the same thing, right? But now I'm going to increase the wave vector k0. And you might wonder, well, what will that do to my packet? So here is my packet before I increased k, so he's just moving along. Now if I increase k, this is what I see. And I hope you can notice that what's happening is it's just moving much more quickly now. And that's because this k naught corresponds to the momentum of my particle, and I've increased my momentum. Remember, it corresponds via the relation p equals h bar times k naught. Now, we can try something else. So I'm going to go back to packet number 2. So I'm going to have my original packet now. So it's my Gaussian, which has some momentum. It's going to be the slower amount of momentum. But the change is now I'm going to add not just a particle in free space, but now v of x is not going to be just constant everywhere or 0, right? But now it's going to have some shape to it. And let's see if you guys can guess. So there's going to be some v of x. From looking at the behavior of my wave packet, let's see if we can try to guess what the actual potential is that this wave packet must be feeling. So once again, let me go back first to video number 2. So I'm starting with this packet now, which will just, move along. As before, you'll see it moving and spreading, but then I've done something to the potential somewhere around location number 12. So let's go up to video number 4. That's 3. Here's 4. Whoa, look at that. What happened here? So let's see. So we start off the same. Here, I can move it by hand, and you can notice the time clicks over here. So as I move it along by hand, you'll notice it's just moving along just fine, spreading a little bit and moving, right, as I go back and forth. But then when his little edge here hits 12, that's where interesting things start to happen. The first thing I notice is I start getting like bumpy waves and rapid oscillations just around 12, right? And that's a clear sign of what's called interference among waves, right? So there's some kind of wave interference happening just around 12. But as time goes on, notice that I get more of this interference, and then after a while, what you find is somewhere around here, suddenly I now have 2 Gaussian packets, right? And one of these packets then continues moving along to the right. You might notice, by the way, that it's moving more slowly than the packets seem to move on this side. Whereas on this side, you notice I now have a what looks like a wave reflection. And of course, this little piece is just where, again, I've gone over the edge of my boundary conditions. So this is a very different type of potential. If we ignore the interference region for a second, I have got 2 packets now propagating. And as I've said, you can see this one on the right here moves slowly compared to the one on the left. So I know the speeds are slower over here on the right. So what that means is if I have a certain amount of energy E for my particle, it's coming in, right, with a certain amount of E, traveling along, and then it must see a sudden increase in the potential. Because the difference, E minus V, this difference here, E minus V, that represents the kinetic energy. So there was a sudden change in the velocity of the particle at this location around 12. And that sudden change resulted in the packet traveling more slowly once it makes it across. But we see something else, which is very characteristic of wave phenomena. We most definitely are getting some kind of a reflection at that special location, number 12. And that's what we normally see, remember, from your waves classes. Whenever there's a sudden change in the propagation medium, like if you had a light string connected to a heavy string, you should expect an incoming wave packet to generate a transmitted wave and a reflected wave. And that's exactly what we are seeing here. Now, the question, though, is, well, what does this mean in our case? It can't mean that I've got a particle here, right, that suddenly my particle, my electron, say, splits into 2 electrons. It looks like that in the picture, but I want to emphasize we are not splitting particles when we get this reflection. It's not particles that are splitting, right? But what we are really plotting is probabilities. So it's the probabilities that are splitting. What this really means is that some particles, there's some probability that the particle just continues along, and some probability that it reflects. So these are, very different types of behavior that we can get when we have just a simple Gaussian packet traveling either through free space, as we've been discussing earlier, or when it hits a sudden bump in potential and then continues moving along.